All right, so let's use Hess's law. Okay, again, we're looking at our enthalpy as a state function. So rather than looking at things being formed from their lowest state, we're going to look at a reaction in terms of other enthalpies of reactions. And if we combine these individual reactions in a way that we get our overall reaction, we can determine our delta H of that reaction. So basically what's happening is it doesn't matter if we take our reaction going directly from our reactants to our products. We can go from our reactants to multiple independent, not independent, but multiple intermediate species and then end up at our products. And the enthalpy is still the same because it's a state function. It doesn't matter the pathway that we take. It's just dependent on where we start and where we finish. So when we're using our enthalpy values of reactions, we want to make sure that we remember the rules that we established. And these rules were from section 6.4 or page 3 of our notes. So if we look back to page 3, 3 things we had to keep in mind: that states make a difference, so we need to make sure that we pay attention to the particular states in our reactions that we use. Delta H changes with quantity, so if we need to change our total coefficients in a reaction, if say we multiply all of our coefficients by 2, then we have to also multiply our delta H value by 2. The other thing is that if we reverse our reaction, we reverse the sign of delta H. So if we flip-flop this reaction, okay, from where we did up here, we flip the sign of our delta H value. So what we do then is essentially it's kind of a logic problem, or you could think of it as piecing a puzzle together. But we want to, in our example here, is calculate the standard enthalpy of formation of CS2 as a liquid, and we're given these 3 equations. So first of all, we want to figure out what is our overall equation that we're after. Our goal is we want to form this from the lowest state, the lowest energy state of each of our items that we're working with. So we're working with carbon and we're working with sulfur. Okay, remember from the previous video that carbon in its graphite form is the lowest energy form of that, and sulfur is in its rhombic form. So we combine these two to form CS2 as a liquid, and we want this balanced, so we need to start out with 2 sulfur rhombics. We want to know what is delta H for this reaction. Now, from the previous video, what we could do is we can look this up in a table. But that's not the point of what we're trying to do with this example. This example, we're going to use our 3 equations here, combine them in a way that overall we end up getting this equation. And as long as we keep in mind our rules for working with thermal equations, we'll be able to combine our delta H of our reactions to get our overall delta H value. To do this, some people have an eye for it, other people don't, and they have to work a little harder at it. But what you want to do is work through lots of problems, so do lots of practice, which is why you have quite a few questions on your sapling homework. And there will also be a question working through this concept on the activity, which I will give you on Tuesday. So usually how I go about this is I pick two equations to start with, and I combine them so that it starts to get me in the correct direction. So I notice I need, what do I need? I need 1 carbon graphite in my reactants, and I need 2 sulfur rhombics also in my reactants. So if I look at my 3 equations, the only equations that deal with graphite and sulfur rhombic are the first 2. Okay, so that's where I have to get my reactants from. So I'm going to take this reaction here straight up. I'm going to write that as is, and I'm going to combine it with 2 times the second reaction. That way I'll get my 1 carbon graphite and my 2 sulfur rhombics. And then I'll add those 2 together and use my delta H's appropriately. And then from there, we'll figure out what else we need to do in order to get our overall equation. So I'm going to start again with this first equation straight up. No changes to it. I'm just essentially going to recopy it down below. So I took my first equation. Now I'm going to take the second equation and I'm going to multiply it by 2 because in the end I need 2 sulfur rhombics. Okay, and the only way that I'm going to get those is by multiplying this by 2. So I have 2 sulfur rhombic, 2 oxygen gas, and 2 sulfur dioxide. If I multiply my entire reaction by 2, I need to also multiply my delta H by 2. And I didn't reverse the equation, so I leave my negative sign intact. So I'm going to add these 2 equations together and then evaluate what I need to get rid of in order to accomplish my overall reaction. So I have C graphite plus 2 sulfur rhombic, and I have 3 oxygens total. In my products, I have carbon dioxide and 2 sulfur dioxides. And then what I'm going to do is I'm going to add my delta H's together. So I have negative 393.5 plus 2 times negative 296.1. So my delta H so far is negative 985.7. And kilojoules per mole. So looking at my overall equation, I have my carbon graphite, I have my 2 sulfur rhombics, but I don't have my carbon disulfide, okay, my CS2. I don't have that in my products, and I have these extra things in my reactants and products. So I need to get rid of 3 oxygens. I need to get rid of my carbon dioxide in my products, and I need to get rid of my 2 sulfur dioxides. I need to also gain a CS2 in my products. So if we look at this third equation here, I have 3 oxygen molecules, okay, or 3 moles of oxygen. And then on the opposite side, I have carbon dioxide and 2 sulfur dioxides. If I flip-flop this, I'll end up with my oxygens on my product side, which would cancel out these oxygens here. These two would go into the reactants, which would cancel out my reactant or my products here. And when we flip this then goes into the products, which then gets me my CS2 for my product. So I'm going to flip-flop this equation, and when I flip-flop this, I need to flip the sign of my delta H of that reaction. So my products here become my reactants. So I have CO2 as a gas and 2SO2 as a gas. And that's going to now form, I'm going to take my reactants now and put them as products. CS2 as a liquid and 3 oxygen as a gas. My 3 oxygens cancel, my CO2 cancels, and my 2SO2 also cancel. So overall, I'm left with C graphite plus 2S rhombic going to form CS2 as a liquid. For my delta H value here, I flip-flopped this equation. So my delta H for that component of it is going to be positive 1072 kilojoules per mole. So I add these two together. Add 1072. My delta H then for this reaction is 86.3 kilojoules per mole. My final answer. So my best suggestion for you is to work through lots of examples using this concept of Hess's law. Okay, so work through the examples in your book and look at the worked out examples so you already have something to compare your answers to. Then work through the examples in the back of your chapter. And Sapling also has quite a few questions working through these types of examples. So lots of opportunity to get some practice. On Tuesday, like I said, I'll have an example on the activity for you to do. So lots and lots of practice is the key.